Hi guys, in this video we're going to look at electrical transformers. We're going to talk about the problem with transporting current, how transformers fix this problem using the electromagnetic effect, and then we're going to go into some hardcore physics calculations and then talk briefly about efficiency. The problem with transporting current is that no matter how good a resistor, it's not going to be perfect. So we use copper wire, which is fine for current around your house and stuff like that, but over a long distance, the resistance of that copper wire adds up, and the amount of current that you can put through it is limited, leading to a lot of inefficiency. And this energy loss can be through heat. So for example, an incandescent light is just a conductor that has a current going through it. Now it's a very thin wire, so that current going through it is being lost as light energy and heat energy. Now this is something that you do want in a light. Well, you don't want the heat, but you do want the light, but it's not something that you want when you've got a power line trying to get the power from the power plant to your house. So we can't then go, oh well, we'll just have a really big wire to get all that current through or all those amps through, because then say we've got a copper wire that's a meter in diameter, that's a huge amount of copper, so that's going to be really expensive. Fortunately, one of the good things about alternating current is it's fairly easy to use a transformer to step up the voltage, lowering the current at the power source, and then step down the voltage, raising the current at the destination. So we've got two types of transformers here. We can go from low voltage, high current to high voltage, low current, or other way, high voltage, low current to low voltage, high current. And these are what we refer to step up and step down transformers. Electrical transformers make use of the electromagnetic effect. And you don't need to know much about this, but just know that electricity or electrical energy and magnetic fields are related to each other. So if you've got a electrical current moving through a wire, it's going to create a magnetic field, and similarly a moving magnetic field is going to induce a current. And induce is just another word for make in a wire. So an example here is we've got a battery. The battery has a current running through that copper wire there that's wrapped around a nail. This is going to create what we refer to as an electromagnet, and you'd be able to actually pick up that smaller nail with the big nail. Now this is for a direct current, so the pole stays in one direction. With an alternating current, that north and south pole created by the electric current flips backwards and forwards 50 times per second, and this building and collapsing current is what then induces the current. Building and collapsing magnetic field rather is what induces the current in the transformer. And that's basically how a transformer works, through what we refer to as mutual induction. So we have the wire curled around here with the current coming in. That induces a magnetic field in this copper ring. The copper ring, or the moving magnetic field in the copper ring, then induces an electrical current in this a wire that's round around this side. Now this is a ring shape of steel or a ferrous metal. This is one configuration. There are others, but they basically work the same. And how many turns there are on this side compared to this side determines the change in voltage or current, whether it's going to go up or down. I will now get into a few calculations on how we do that. But first, just to define some terms. So we have here the one side is the incoming side, and the two side is the outgoing side. So the voltage is being produced here, say at the power plant, ready to be transported across the high voltage power wires. So we've got here the number of turns on the one side, the number of turns on the two side, voltage on the one side, voltage on the two side, and the current on the one side and current on the two side. So we'll use these terms in the calculations that are coming up shortly. Okay, so I'm going to start off with talking about the change in voltage. So here the number of turns is directly proportional to the voltage on both sides. So it can be put into this formula where the number coming out divided by the number coming in equals the voltage coming out divided by the voltage coming in. Now you can have this the other way around with the 1s on the top and the 2s on the bottom, doesn't matter. The important thing is that both you have the same number on the top, whether it's the 2s or the 1s. So let's have a look at an example of this. So here we can see that we've got 5 turns on N1 and 10 turns on N2. And for ease of calculation, we're going to say that we have 100 volts coming through this primary side. So we get 10 divided by 5 and V2 divided by 100. So we times both sides by 100. V2 is going to be 100 times 10 on 5, which is 2. 100 times 2 is 200, and it's voltage, so we'll give it the units of V. Current, on the other hand, is inversely proportional to the number of turns. What this means is that when the voltage, you had the 1s and the 2s either on the top or on the bottom, in this case the 1s and the 2s are crossing over. So you have got 1 on this side and 2 on this side. Again, you can have these the other way around, so you could have 2 here and 1 here and here, doesn't matter, but as long as they're on different sides. So again, on this side we've got 5, and on this side we've got 10 turns. And again, we're going to use 100. This time we're talking about current, so that's 100 amps coming in. So we just plug that into the equation, giving us 5 on 10 equals the current coming out divided by 100 times 100 by times both sides by 100, giving us 100 times 5 on 10, which is a half, equals the current. So that comes out as 50, and then we'll put our units of amps in there. Okay, so it's fairly easy to use this formula. Okay, I'm going to briefly talk about power now, and I know that this is a new term, but it's a fairly simple one. So the amount of power in a circuit is defined as the voltage times the current. Now, and it's measured in the unit of watts. So in theory, on the incoming side, the power should be the same as on the outgoing side. So the voltage 1 times current 1 equals power, which will equal the voltage 2 times the current 2. And using the numbers that we got, we had 100 volts and 100 amps come in, and 200 volts and 50 amps come out, and both of these equal 1000 watts, giving us the same power on both sides. Now, I say in theory, this is never going to happen. You're never going to have a 100% efficient conversion of power in that way. Some of it is going to be lost to the environment, and that can be through various ways. The resistance in the coils, the resistance to a magnetic field in the actual ring itself. But just as an example of loss of power, this is a little diagram here showing an incandescent lamp again. So to get 1.35 joules of power out of it, out of the actual light, it takes 188 joules at the actual power station. So converting from coal into electricity is very poor or very inefficient thing to start with. So at the plant, you immediately are going to lose a whole heap of that power. Then once you get to the distribution grid, you've got step-up transformers to get it to high voltage, step-down transformers to get it back to voltage that we can work with in the home. And then when you actually plug your appliance in, you're losing efficiency there as well. In this video, we've looked at transporting current and why we use high voltage power lines to transport current. We've talked about transformers as the way we turn a high current power into a high voltage power with a low current, making it easy to transport. These use the electromagnetic effect because electricity and magnetism are related to each other. And we looked at calculations on calculating the change in voltage, calculating the change in current, as well as briefly talking about power and efficiency. Thanks for watching, guys. Peace out.